Greeting everyone, a wonderful day. Hi, I'm Harvey J. Tiang and I will discuss problem 7.11b found at your exercise on chapter 7 of the physical chemistry book of Atkins 8th edition. Here is our problem. You can pause the video for you to have the time to read the whole problem. For our given, you have the pressure of ammonium chloride at 427 degrees Celsius to be 608 kilopascals, and for the temperature 459 degrees Celsius, we have 1115 kilopascals. Our required is we need to find the equilibrium constant at the temperatures 427 degrees Celsius and 459 degrees Celsius. We are also required to find the standard reaction Gibbs energy, the reaction enthalpy, and the standard reaction entropy. We are given with the equilibrium equation for our solution. Then we know that for our system, the NH4ClS, that the total pressure is just equal to the partial pressure of the NH3 gas plus the partial pressure of the HCl gas. Assuming that the NH4Cl solid dissociate into two equal molar fractions, therefore the partial pressure of NH3 should be equal to the partial pressure of HCl. Therefore, our total pressure is just equal to twice the partial pressure of NH3. Then rearranging the equation, we have that the partial pressure of NH3 is just equal to the total pressure P over 2. For our solution, we could use equation 7.16 to get our equilibrium constant. This symbol denotes the product of all of this term, in which A for gases is just equal to the partial pressure over the normal pressure, which is equal to 1 bar or 100 kilopascals. Then we have this expression. Then we know that the partial pressure of NH3 is just equal to the partial pressure of HCl. So we have this expression. Then we know that the partial pressure of NH3 is just equal to P over 2. So we have 1/4 times P over P normal squared. So substituting the value for the partial pressure or the total pressure P of that species. So at 427 degrees Celsius, we have K is just equal to 1/4 times 608 over 100 squared to give us the value of 9.24. At 459 degrees Celsius, using the same process, we get that the equilibrium constant at that temperature is just equal to 31.08. For letter B, we could just use equation 7.8, in which the standard reaction Gibbs energy is just equal to negative RT ln K, in which our temperature is set to be 427 degrees Celsius or about 700 Kelvin. Then substituting the values, we get that our standard reaction Gibbs energy is just equal to negative 12.9 kilojoules per mole. For letter C, we could use equation 7.25 to get the standard reaction enthalpy, in which the standard reaction enthalpy is just equal to R ln K prime over K, in which the K prime is for the temperature of 732 Kelvin and the K is for 700 Kelvin. Substituting the values, we get that our standard reaction enthalpy is just equal to 161 kilojoules per mole. And lastly, for letter D, we could use the expression for the standard reaction Gibbs energy, which is just equal to the standard reaction enthalpy minus temperature times the standard reaction entropy. Rearranging the equation, we could get this expression for the standard reaction entropy. Then substituting the values, we get the value for the standard reaction entropy to be 248 joules per Kelvin mole. And that's all for my presentation. Thank you and have a good day.